all around us. We can't see them because our eyes don't go that small. Remember, our eyes only see from, what, 450 nanometers to 700? We've got a very small range of visual cues. But we do see in the nanometer range, but atoms are smaller than it is. Okay. So how do we explain, and right, this is all made up, right? This is just man making up things that seem to be rules in the universe that we live in and help us explain the universe. So we've all decided that the periodic table has elements on it. Each one of those elements represents a different number of protons and a different number of electrons. And how did we find out what that means? Well, one of the ways is we described what is light. So we did a lab on light, right? And we talked about wavelength and frequency and comparing those two relationships, right? They're inverse relationships. The longer the wavelength, the shorter the frequency. The shorter the frequency, the longer the wavelength. Frequency and energy are directly related. So in the 1800s, that's all we had. All we had was light, and we had refracting it through glass. Remember, they were really good at stained glass in churches and things, and light would come in and they could light up the interior of a building using different colored glass. And then why do atoms emit only certain colors? We weren't really sure. 1900s, quantum mechanics, then that was when we really made the big jump in the 1920s, thanks to Einstein and other people like him. So we know that wave crests passing a point of time. So if you sit here, waves come just like at the beach, boom, boom, boom. We get to see the beach a lot, most of us driving by, even just right out here. Per second, right? How fast does something go by per second? That's frequency. So S minus 1. Right? 1 cycle per second. So when we talk about energy and waves, we also think of that as electricity, right? Electricity is 60 cycles per second from a standing point, which means 60 times. That wave goes through there 60 times. So electricity is electrons moving 60 times per second, or 120 times per second. Your flicker rate on your screen, right, on your computer screen, 60 cycles per second as well. And we call that a hertz, 1 second. So the distance, the wavelength times the frequency, is the wave velocity. That's how fast it moves. Okay, that's not a big deal. Amplitude is how high it is, right? How high above this central plane the wave goes. The wavelength is the distance between the two peaks as it travels past a certain point. And that's what we say. So the higher the amplitude, the brighter the light. The lower the amplitude, the dimmer the light. Wavelength, again, is the distance between crests. And you can measure it between any two crests. You measure it at the low point or at the high point, it doesn't matter. It's going to be the same. So we talked about electromagnetic waves before. And again, we're going to mark the wavelengths. And then we have this line above the node, right? Plus and minus. That's how we know it's a wave. We're not going to be tested on that either. But we need to know that the wavelength times the frequency equals the speed of light. All of these electromagnetic waves, which are beyond our senses, right? They're not just the ones we can see. They're all the waves throughout the entire spectrum. Everything we have is energy, right? When we stand next to each other, we have energy that we transmit, and it either overlaps, making us feel good, or it has interference that makes us feel poorly, right? As human beings, right? And you say people have bad energy. Well, bad compared to who, right? Genghis Khan probably had bad energy, but you couldn't stop him. You know, people say that the Trumpster has bad energy, but no one stops them. Just saying, it's you have to be careful with who you share your energy with and why, because it can affect you, right? It can affect the way you conduct yourself or what's in your mind or how you move. Right? And so when we give a test on material, we want to make sure you are exposed to that material. I don't want to have it come as a surprise. I'm not trying to use my energy to pull you down. I'm trying to use my energy to lift you up, right? And again, it cycles, right? I'm not always at the high peak. I try to be on the high peak when I get here, and I try to stay there the whole time. But it is a wave, and so when it's going on this side, right? That's why people like to medicate and stay at this level. But how real is that?
What's the fun in that?
What's the fun? So, long wavelength versus short wavelength. So that also happens, right? Our phones are constantly emitting a wavelength, right? And we keep increasing that wave. Do we increase the wavelength or do we increase the energy? We keep increasing the energy, so we keep shortening the wavelength, right? We're now 5 gigahertz, holding it right next to us all the time. The thing is, the higher the energy, the deeper it goes into the more penetration it has into your skin. We don't know what the effects are because we've never held anybody down and slammed them with radio waves, but we're doing it now, but self-inflicted. Okay. What else? So kilohertz, AM radio waves. So in the old days, we'd have AM radio in our car, and it was at a certain kilohertz, right? 10 to the third, right? 10 to the third hertz. So 1,000 cycles per second. Megahertz, 10 to the sixth. That's 100,000 cycles per second. Gigahertz, now we're talking, what, 12? Terahertz, that's way more than I know what that is. 10 to the 14th, here we are. Infrared, visible light, ultraviolet. So now we're beyond the spectrum that we can see. But we can use devices to give us that heat signature, right? Infrared's heat signature. Hunters use it at night. 10 to the 15th, X-rays. So this is just 10 times, right? 10 times different. And that can show us our bones. And when X-rays first came out, when Röntgen in 1895 made it a deal, and then we learned to harness it, they would put them in stores, and people would walk in and X-ray their feet all the time. Incidence of cancer went up dramatically. So KUWR, which is the
Off topic. I know Bell Labs has been around for forever. What exactly did they do? Because you gave them.
They're just an example of people that operate in terahertz frequency.
Okay.
So if you want more information on that, you'll have to
Look it up.
Okay. So in the old days, there was the telephone company. They were the only ones that even had access to high. Bell Labs was the development portion of the phone company.
Yeah. They were in New York since like the 20s, right?
Yeah, they've been around a while.
Yeah.
I don't know their whole history, but they would recruit the brightest and the best scientific minds, and they're the ones who ended up developing, the relay stations and all that kind of thing. So I'm not going to go into a history. That's another day. What is the wavelength? That's KUWR is the radio station in Wyoming, and it broadcasts on 91.9 FM. And what is the wavelength? The wavelength is wavelength times frequency, okay? What do we have? Equals the speed of light. Speed of light is 3.0 times 10 to the 8th meters per second. And then the frequency is FM, so that's 10 to the 7th. 9.19 times 10 to the 7th from 9.19. And this is frequency modulation, which means as you send the signal, the frequency changes, right? Well, we modulate the frequency, which means we change the frequency. So if you, AM is amplitude modulation, which means we change the height of the wave, the amplitude. This is the frequency. So when we do that math, we solve for lambda, which is the wavelength, and we get 3.26 meters. So pretty straightforward. You just plug in for lambda and frequency, or wavelength and frequency, and speed of light. If you have two, you can always solve for one. And if you were given a problem like this, you would be given the frequency in per second, cycles per second.
What's on the V right there? Is that just a comma next to the wavelength and
Right
on
here?
the very end? Yeah, what is that?
Yeah, that's
Just a comma.
lambda equals C divided by V, comma, wavelength equals
Okay.
C divided by V.
Okay, thank you.
You're welcome. Okay, so we have lots of regions. We went over that before: gamma, X-ray. When we have ultraviolet, infrared, microwave, radio frequency. So that we go from these little tiny wavelengths of 10 to the minus 2 all the way up to 10 to the 12th. That's a big wave, right? 10 to the 12th. In nanometers, though, it's not that big. Because the nanometers, what, 10 to the minus 9? So 10 to the 3, right, which is 1,000 nanometers, which would be 10 to the minus 6. We couldn't even see it. So even though it's a big wave in terms of nanometers, the wavelength isn't really that long. Okay. And visible light, remember the rainbow, eat Skittles. Roy G. Biv, it's a poor mnemonic, and that's not even how you say it. So, mnemonic.
Mnemonic.
When I was growing up, we said mnemonic, but now they say mnemonic. And I can't find it pronounced anywhere else differently now.
Mnemonic.
Okay, so light also doesn't just act like a wave. That's one way. It also acts like a particle. It's called the dual nature of light. And the problem came from black body radiation. So light energy is proportional to intensity and varies continuously. Can't explain black body radiation. This is a classical physics problem. We don't need to worry about that, but Max Planck figured it out. Thanks, Max. And he gave us E, energy equals HV. So Planck's constant is the H, and this is frequency. So knowing Planck's constant, which you can solve mathematically, and sometimes if you take a physics class for a year, the year physics series, you'll have to solve this. I know I did. You have to solve for Planck's constant. We're not doing that. This isn't that class. This is just HV. So we're going to give you Planck's constant to find the energy. And why is the energy important? Well, because different levels of energy are based on different frequencies, right? And if we have the frequency, we can just use Planck's constant. So when we went back to this problem back here, come on. Really? Right here, we're given 91.9 FM, right? That is a frequency. So we can take that 9.19 times 10 to the 7th seconds, and we can plug it into energy equals Planck's constant. So we could do Planck's constant, 10 to the minus 34 times 10 to the 7th, get an energy around, what, 10 to the minus 27 joules, and seconds would cancel out. Because, and I know you're not seeing that, I'm not showing you, but it's a thought idea, right? We're gonna replace this frequency, we're gonna place it with 9.19 times 10 to the 7th meters. Seconds per seconds. And then we're gonna cancel that out with this Planck's constant. We're gonna end up with the number of joules, 10 to the minus 7, 10 to the 7th, 10 to the minus 34 minus, or plus 10 to the 7th is about minus 27, so that's where we get that. And that just tells us where radio operates, Katie. Highly. Yeah, what is black body radiation? Beats me. It's a classical physics problem. So you have this body that absorbs energy, and how do we explain that? How do we explain that what's happening in that black box? That's the question. But I didn't even look at it, so I don't know what it is. There's a lot of stuff I don't know. Radiation, or remember, I probably knew at one time, like the last time I did this. Radiation, I wasn't even going to talk about any of this, but I like it. So there's visible light, right? We saw this, right? We saw evidence of this. You plug in energy, you see the decay here, radiation in nanometers. The best part is, this guy, the Planck guy, he didn't believe his own math. So it was just a fairy tale. All this is just a fairy tale of man explaining things that make sense and the math behind it. And the math works, right? But there's a whole new group going, we don't need the math to do anything. We just build stuff. So we'll see. See who's right. So there's this photoelectric effect as well. So you have incident light hitting a surface, and it gives off energy, and it ejects electrons, right? So we know that, right? We've done that ourselves. We've taken a piece of metal and we've dipped it in hydrochloric acid, and we've changed it, right? It gave up electrons. But then we can also do it with light, remember, because that's energy, and HV is the energy. Planck's constant times the frequency. We're not going to be tested on this either. It's just the idea. So this is how a photocell works, right? You have a metal surface, you shine light on it, it injects electrons, you create a circuit with a switch. That's another class too. It's just exposure right now. Observe, only get current frequency. Only get current if the frequency of incident light is above a threshold level. Remember, all our experiences with electrons, right? They go from one energy level to another. They don't ramp up, they jump, right? So you're at level 1, you put energy in, you go to level 2. If you go to level 2, you can come back down to level 1. If you jump up to level 4, you can come back to level 3, level 2, level 1, or you can just jump from 4 to 1, right? So you have to have enough energy to make a full transition from one state to another in order to make a circuit. And so more frequency stuff. This is what Einstein did. Kinetic energy of emitted electrons versus frequency. It makes sense, right? The more energy you pump in there, the higher the frequency. Okay, that's the correlation, right? X versus Y. The higher the Y value, the farther the X increase. He was only 25 years old. Right, so he was just, like, I still don't understand what he did, and I'm pushing 3 times that. So, thanks, bud. So, light energy is delivered in packets of energy. We call them photons. HV again. Look at that, energy. Planck's constant versus frequency. So all I did was rework what Planck had already done. The threshold frequency is VO, which is the initial, and EO, which is the initial. So you're changing this frequency, and then boom, it just jumps. But I don't know, it's too complicated for me. But we can calculate the energy. It's pretty straightforward, even if we don't understand all the quantum mechanical devices that Einstein and his colleagues used. And this is one of them. Calculate the energy in joules of a photon of violet light that has a frequency of 6.15 times 10 to the minus 14. So we're going to plug this in to what? E equals HV.
Would this be something that's on the test?
This would be exactly something that's on the test.
Thank you.
This is good. Since we're only covering test material, this is going to be the thing, and that's going to be on the practice test.
Thank you.
Okay. So E equals HV. H is Planck's constant. 6.626 times 10 to the minus 34 joules per second. 6.15 times 10 to the 14 seconds minus 1, which means 1 over seconds, right? Equals 4.07 times 10 to the minus 19th joule photons. And remember, this is in the packet, right? So this is on the website, on Canvas. It's downloadable.
This slide?
Yeah, all these slides.
No, I'm filling mine out from the canvas
Oh,
right now.
okay.
It's blank.
Oh, right, this part isn't
Yeah,
on there.
so I'm just.
Right, I'm just saying the slides are.
Oh, yeah, yeah, I have the slides from there,
You
yeah.
got your words, not the math.
Right, I didn't give you the math.
So, almost done there.
But we all have the technology to be able to either take a picture of the slide or write it down.
Yes.
Because believe me, if I had to text someone right now, you guys won't be able to do it. A laser produces red light of wavelength 632.8 nanometers. Bless you. 632.8 nanometers. Remember, 10 to the minus 9 meters. Calculate the energy in kilojoules of 1 mole of photons of this red light. So when we think photons, just think energy equals hv, and boom, you're right there. Sometimes we don't have the V, so we have to use the formula. Get away from me there, Brenda?
Yeah.
Very good.
Thanks.
Frequency equals speed of light divided by wavelength. So we just substituted that there because that's what we have.
Is it,
Solve for.
so it's always 6.626 times 10 to the negative 34.
Planck's constant.
Thank you.
Yeah. And, yeah. So it will also be on the back page of the exam. I mean, because again, it's a memorizable thing, and if you do enough problems with it, you'll remember it. But if you don't, you should be able to at least recognize it. That's Planck's constant. What's that H? I don't know. That's Planck's constant. It's on the back page right there under the list of things you might want to use for this test. And then, yeah, and then C is going to be back there too, right? Even though the speed of light is 3.0 times 10 to the 8 meters per second. Right? It's pretty fast. If you ran that fast, you'd tear it up.
Thank you.
Get fast. Okay. And so if you continue on and do the math, you end up with 189 kilojoules per mole, right? 1 mole, right, that's where we bring in back Avogadro's number, right? Because we have a certain amount that we calculated, the energy of 1 photon, but we don't just have 1 photon, we have a mole of photons, right? Or 6.022 times 10 to the 23rd photons. So getting that relationship between 1 and a mole, and how to go from 1 photon to a mole of photons, you have to use Avogadro's number. You have to expand your vocabulary to include Avogadro's number.
Okay.
And then try to remember that Avogadro's number is not 34, but 23.
23.
Okay. I can go.
Thank you.
So line spectra, holes in the rainbow, this is how we figured it out. I'm not gonna worry about that. This is what we did in class. Rydberg, this is what we need right here. There's gonna be a Rydberg problem on there as well.
Okay.
Right? We did that in lab, so we should be able to do it. We should be able to reproduce that. Was that experiment 9, the disaster experiment?
Yes.
Yes.
Yeah.
So
Yeah.
we can't do that.
Okay, well, we can.
It was take.
So when we look through the slits, we got a number. Yes,
So why did we do lab night for learning this?
because of COVID
Yeah.
and the Russians.
We lost time, but we gained time.
The
The
Russians.
Russians.
Yeah, the Russians invaded it, threw everything off. Man. And COVID as well. 2 weeks. Why did we do it before we covered it? Because I did a lecture before we did this on this.
We did.
Right in class, before we did the lab. Should be a review. A more detailed review, but I did present this before, if you were in lab that day. So Rydberg constant, and then of course I went on and on and on, and found out we had 3 different lab books all semester, which I still haven't recovered from that either. Neither of you.
No.
No, we
Went
haven't.
over-
We haven't.
So there's hope, that's what I'm saying.
There is hope. Let's go.
1 over lambda. Right. And lambda is wavelength.
Yeah.
So if we know the wavelength, when we looked at the little slit, we got a number in 9, right? And we wrote that number down, and we used it to calculate the line spectra, right? Therefore, our little plot on 9. Okay. Well, anyway, this is a constant, and this is the energy gap that when we excite the photon and it drops down. And this is the, which one? Do we remember? Does anyone remember? Oh, look, where N2 is greater than N1,
Oh.
right? So N2 would be the highest point where it drops back down in the emission spectrum. The visible lines, you guys remember this? You put energy in, you take it from the ground state. The one site we can see is the Balmer series, and it's any transition between energy level 5, which would be on our periodic table, right? Row 5, down to energy level 2, which would be like what? Helium, right? The one, second column. So you can see those transitions, 5 to 4, 5 to 3, 5 to 2, you can see all those. And we can calculate the energy or wavelength associated, right? Rydberg's got a constant, it's R, it's a number. We're gonna plug that in, and then we're gonna probably solve for one of these. That's a little bit harder. Nathan was nice enough to post how to do that and a program that does it for you on the discussion board, including how he solved this problem in lab. So all of you should be able to solve this problem in lab, by the way, because that's on the discussion board. If you look at the discussion board, which is part of the class, which is part of your responsibility of being here, if you want to get credit for all the time you've already spent, because you've spent a lot of time already. We only have 5 meetings left after today.
I clicked on
it's gonna-
that link though,
right.
and
What?
did anyone open that link?
Mm-hmm.
Did it take you somewhere?
It took me where he sent it.
Okay. Maybe it's operator error.
Just mapway.com.
Oh, it took me to like a.
Yeah, I just typed it in.
Okay, never mind, you're good.
Can I?
I'm sorry, I was just wondering if anyone else had an issue. I had an issue with it. Sorry.
So we're going to use Rydberg equation. Make sure you know how to do that. That's going to be one of the problems. And if I don't give you the problem in class, find one, like in the lab book that you had to solve. That might be the one that I use, right? Because it's drawing from material you've been exposed to and you're responsible for. And I'll probably give you one of the practices. All right, Niels Bohr, he developed the model that we are looking for now, the modern model of the atom and orbitals. So electrons can only occupy certain orbits, stationary states. They don't suffer orbit decay. Now we know this isn't true either, right? Atoms don't radiate from a stationary state. Energy absorbed or emitted by H atoms is due to changing between stationary states of electron energy levels are quantized. Okay, so now let's look at what we're really talking about. We're talking about one element with one electron. This is the level of ability that we have to determine what's really going on. Now, we do a lot of other math to say, oh, we can handle 2-body problems, 3-body problems, but we have to set a lot of things to 0. And what happens is when we do that, we don't know what's going on. We set something to 0 and we solve for that. Then we set something else to 0 and we solve for that. And then we say, based on these 2 interactions, we have a constant. So we're looking at a system, but we're setting everything equal to 0. That's like the physicist's dream, right? We set everything to 0 except for the one thing we want to know. And then we say that effect is due to that 0, but they're all in combination all the time. And then we also look at the difference between, right, how much does it contribute? So if I weigh like 250, right, and I say, oh, I lost a pound. 250, 249, 251, not really a big deal. But if I lost 50 pounds, the difference between 200 and 300, pretty big deal, right? But that 1 pound, that could be variance on the scale, especially if I said, like I was 250.0, and then it was only 250.1 or 249.9, right? the contribution of that tenth has nothing to do with the overall total. Well, that's kind of what's going on with a lot of these energy states, right? Once we start getting farther away from the central atom, right, or the element of interest, the energy level to hold it there is much higher, but it's also easier to remove. And we're going to keep that in mind when we start talking about ionization and electrons leaving an atom, right? All these metals, column 1, column 2, they lose electrons. It takes a little bit of energy for them to leave. And then the second electron takes even more energy because the energy levels are quantized. So energy of a photon equals E state A minus state B, which is HV, right? So if we have two different states, we still know it's Planck's constant times frequency, and we can replace frequency with wavelength by doing C over lambda. So this is the other thing, right? So this is how we solve for B. We're not going to do that. So there's a break. But those of you that need to understand that we can use this B value because, again, everything's quantized. So that's the step. B is the step where B equals 2.18 times 10 to the minus 18 joules. And again, what does this look like? This looks like the Rydberg equation, right? Instead of R, you have a B. Okay. So let's not really worry about that one. We do know, we've seen that, right? We've seen that we have absorption. They absorb energy to go from level 2 to level 5, and then they emit energy to go from 5 to 2. Electrons does. And so this is the point. This is real, right? We know this. We found electrons. We know electrons are real, right? We're not just describing electrons. They're actual particles that we can trace and find and measure, and we can change their energies. So it's not empirical. It's not just an idea. It's a real number. So that's kind of cool. All right, so here, how do we use this stuff, which is really, what you want to know. So you calculate the energy change in joules that occurs when an electron falls from the n equals 4 to the n equals 2 energy level in a hydrogen atom. And what is that minus B? What is that? We just got done looking at that, right? That's the Rydberg constant, right? It's the same equation, right? You guys see that? Yeah. And so how do you calculate the energy? So this is the change in energy, right? So you go from one state to another state. Use that B value. But we're not going to do that. So that's okay. And then we calculate the total energy based on H versus the frequency. And how do we get the frequency? Well, we have the energy versus the wavelength, right? So we take Planck's constant, the speed of light, and divide by the change in energy. And that gives us the lambda, 486 nanometers. So this is like when we are trying to explain that little slit of light that we looked at through our spectrophotometer. This is the energy associated with that wavelength of that transition that we saw when we looked through the slit and we got a color. And that's why we were doing all that, so that we could correlate, oh, we're putting energy into an electron, we're making it jump up and then decay back. And when it decays back with the same amount of energy at the same wavelength. Every time. For that particular element and its transition. So when an atom has its electrons in their lowest possible energy level, the atom is in its ground state. So that was just, basically I was only doing this to show you the Rydberg constant, E equals HV, what is it? Lambda, C, and frequency, right? So replacing those things, doing Rydberg equation, doing the energy calculation. That's what I really want you to take out of here. So let's make sure we see that one more time. And so we're gonna do a lot, but we're gonna keep it simple and straight, stay right on what I want you to gather out of all this. So, right, frequency. So you should know, like, here's some words to know. Frequency, amplitude, lambda V equals C. Speed of light, you don't have to memorize, it'll be on your handout, but you should be familiar with it so you know what C is. H is going to be on your handout, Planck's constant. Right? E equals HV, that's the other thing. H, Planck's constant, 6.626 times 10 to the minus 34. Don't even care about the photoelectric effect. If you want to know more about the black box radiation, look it up. I'm going to have to look it up again since I already forgot what it is, because it's been 2 years since I did this. And it didn't come in handy because I didn't prep for this, because I was only going to do this part, right? 1 over lambda, right? 1 over wavelength, which you could replace with what? That speed of light and frequency, right? Okay, so Rydberg, our value is going to be on the list of equations, so you don't have to memorize that, you just have to know how to use it. And I would suggest you manipulate this equation so that you can use it. Like put in a 5, put in a 2, know how it goes. Be able to solve for N2 or N1. I can't emphasize enough that I can't just give you the problem and have you memorize it. It's not that kind of class. I can give you some problems, have you memorize some of them. And then this, it's not going to be on there, right?
T.
All right. So that's that. Oh, yeah, and then there were the practice ones that we practiced, right? I didn't do, where did this come from? Oh, we have more. We have de Broglie. I'm sorry.
You haven't went past beg the question. You stopped at
I'm gonna skip beg the question.
Okay.
What is begging the question? Why do electrons assume these stationary states? Well, they must be what?
Because they're Democrats?
Well, what must happen? They're comfortable there, right? Why do you assume a resting state? Because you're comfortable. And that's what it is. They're comfortable there because of the energy, right? Photons have no mass, but have equivalent momentum. So E equals mc squared. This is back to Einstein and stuff nobody understands, but everybody pretends they do. And it's the basis behind solar sails. Right? So once you get something moving, it stays moving unless there's a frictional force. And we've decided in our infinite knowledge of 5% of the universe that there's no friction in space. I don't know, I haven't been out there. Only a few people have been out there. And more, thanks to Elon Musk, right? For a mere $250,000, you can go up in a penis. Rocket.
What?
No,
Pete Davidson, what did he pay, like $1 million to go? I think
He what?
Pete Davidson.
I thought he only had to pay $250.
I don't know, he paid something.
He probably had to pay extra.
He's going to.
Yeah.
What?
All right, so if light can have particle-like momentum, why can't particles have wavelength momentum? So this is the dual nature of light again. But de Broglie said wavelength equals h over mv. So again, Planck's constant, mv, where particles with mass and velocity have an associated wavelength. So we went from light and photons, which have no mass, right? They're just energy packets, to, wow, we can do the same thing and figure out the wavelength of something with mass, which is very cool. 1929, so before the bomb.
Wait. And these just mass and velocity?
Yeah,
Okay. Times equals that. No. Okay. 1.
so the whole thing is energy, mass times velocity equals energy divided by the speed of light. So we can replace energy with h frequency. So Planck's constant versus frequency over the speed of light. Frequency over the speed of light is 1 over lambda. So mv equals Planck's constant over lambda. Or lambda equals h over mv. Which means that for any wavelength, we have an associated mass and velocity. And it's, when you bring it to this side, it means they are inversely related. So the greater the mass, the smaller the wavelength. And if that turns out to be true, I'll put physics. He did not put physics. What is the wavelength of a 7.26 kilogram bowling ball? 16 pounds traveling at 5.0 meters. So this is bordering very closely on physics, de Broglie, but it is good to know that the wave function even works with mass. And so you do lambda equals h over v, so you put in Planck's constant, you divide by 7.26 times 5.0 meters per second, which is nowhere near the speed of light. I mean, this guy is not rolling that ball that fast. Right? So you get 1.83 times 10 to the minus 35 meters. So when you're rolling a bowling ball down the lane, it has a frequency. 16-pound ball, that's pretty good.
Max weight, ain't it?
Yeah, I think so. I mean, I don't know all the rules of bowling.
I think that's max weight.
So what is the wavelength of an electron traveling at 90% the speed of light? Okay, so electron's mass is very small, right? 10 to the minus 31 kilograms, a very small amount of mass. But we just plug it in. So all we have to do is recognize these different little equations. HV, what's the other one? H over mv equals lambda. Right? It's 3 equations, and they're all derived from each other, and they'll all be on the formula sheet. You just have to put them in the right problem. So if you don't recognize that problem, ask one of your classmates, ask me, ask the discussion board, ask Chem, whatever it takes, right? You can do it.
You know, I bought stocks in Chegg. I'm just kidding. After this class. I'm just kidding. It's very helpful.
It is very helpful.
The explanations
Right.
are great.
Yeah, Nathan.
You mind going backward?
Yes, please. Thank you.
Guys, like, if I thought it was hopeless, I'd just say, wow, it's hopeless. It's not hopeless. You're all really close, right? Because remember, we're adding 10 points. Well, you got to do the work, though. I mean, if you did well on the test, if you didn't do well on the test, but you turned in all your other assignments, that's going to bump your grade up by like 10%. So if you got a 50 on the test, you're already at 60, which means if you do the work. But you don't do the work and you stay at 50, and that's not going to be enough to pass. Right? You got to have at least a 60. Even though the worksheet says 70, really 60s. I mean, not that I'm going overboard this semester, but normally I do. If I threw in the B stuff, that would be overboard. All right, we caught up?
What's pictometers? Is that what it says?
Pico.
Picometers, sorry. I was just glancing at
Not
it.
big of a go.
I like pictometers though.
Pictometers. I just
That's-
glanced at it and.
I think that's what they measure Instagram photos with.
Okay, thank you. Picometers.
Yeah, you'll have to look that up on the worksheet.
Okay.
It's like, I think 10 to the minus 15. Or 12. Something like that. 12 or 15. I never remember that one. I have to look those up because I'm using them. And we're gonna skip all this. Oh, here's another part that I think is. So all these guys worked together. Remember, they didn't work in the same lab necessarily, but they did a lot of communication. And back then, there wasn't a lot of ways to communicate, right? You had to write letters, you had to attend talks,
Oh.
you know. Sometimes it takes 6 months to get from one place to another. So you can't know both the position and the momentum of a particle. This is the uncertainty principle, and everybody should be exposed to this, right? Heisenberg. You can know one, but not the other. So if we stop, freeze time, and I know exactly where you are, I had no idea how fast you were moving. And if I don't freeze time and I watch you move, I have no idea where you are. And me, everything's uncertain. I don't know where you are or how fast you're going, and I don't care. All right, so the change in position times the change in momentum, remember our delta means change, is equal to h over 4 pi. So here's Planck's constant again. And who knows if they tied this number to everything or if the number belongs with everything. So is it mystical? Is it unsettling? Is it a non-deterministic universe? Oh, Alice, you're the one for me. But Bob, it's Bob. In a quantum world, how can we know for sure? Yeah. It's very uncertain. What is the physical meaning of uncertainty? I'm living proof. Observing a small object disturbs its position or trajectory. So in psychology, they say when you study, subject knows they're being studied, it changes the result. Well, the same thing happens here. But does that mean the electron knows it's being studied? Whoa, that's putting a lot on a poor little electron. I mean, it's got barely any mass. 10 to the minus 34 kilograms. So we can only dream of being that thin. Exact frequency, a wave, no position. Inexact frequency, pack the wave in, pack them all together. So this is how we started manipulating things, right? We started manipulating a whole bunch of wavelengths, putting things together. That's what we use now for digital signal processing, right? That's what we're doing with our cell phones. We're taking a bunch of waves of different energies, putting them all together, multiplexing them, and then taking them back apart and decoding them on our phone. Pretty awesome. All from Bell Labs. Schrodinger. So here's another name. So 2 names that I say you should know. Heisenberg. If you know how fast it's going, you don't know where it is. If you know where it is, you don't know how fast it's going. The uncertainty principle. And then Schrodinger. A few days ago, I read with great interest De Broglie, which I finally got a hold of. Right. 1925. What was this?
That's surprising. 32.
29. So Schrodinger finally got this 3 years later. I've been intensely concerned these days with de Broglie's ingenious theory, but it still has some grave difficulties. 1 week, Schrodinger gave a seminar and came up with, skip all this, the wave equation. This changed everything. Because now, with all these, yeah, this is when you do differentiation. Right? So this is the second differential of a wave function. Well, it turns out what that means is, all it really means is we can now guess where the thing is within a certain amount. So this is the probability of finding an electron. That's what Schrodinger did. He took it from we don't know where it is to, oh, we know where it is. But Schrodinger isn't famous for this as much. Well, he's super famous for this. But the cat, the disappearing cat, and anyway, which I really don't know all the details of. It's kind of sketchy. But the electron energies, he came up with a wave function, and that's his big contribution. That's what we use now. All the orbitals that we're going to describe about positions of electrons are the probability that we find that electron in that space. And the shape of those, whether it's a sphere for S, a dumbbell for P, a multi-dumbbell for D, and some weird combination of dumbbells and spheres for F, those are all mathematically defined probabilities. As opposed to the old theory where electrons were just circling around. So when we see a sphere and we say there are 2 electrons in there, it means somewhere within that area there are 2 electrons. We don't know exactly where. And at any given time, they could be right next to each other or opposed. But we're gonna find these numbers that go along with this wave equation will define the parameters of each electron specifically. Okay, that's it for that. Nice. So that's what we're going to do next, which is, yeah, we got plenty of time. What's that? Quantum numbers, I
For those
believe is.
units that look like a backward 6.
I'm sorry.
The last slide.
On the last slide, when we're the.
Oh,
Yeah,
mean on
the
this?
backward 6.
that means the differential. There's a second differential. This is psi. Psi is the wavelength. So this is, you take a differential, which is like a dx, and then you do it again. That's the second differential. Take a differential of a differential. It's a little past Calc 1. It's differential equations, which comes after Calc 3. And before,
Insanity.
well, is it insane or is it real?
No, it's ordered, it's just.
So 3 parts, 3 positional coordinates, and we're gonna call these in space the dimension, right? We have r, theta, and phi. And if you were at Berkeley right now, you'd have to solve this. So their freshman chemistry class solves this.
How do they even know that's real?
Oh, right here. Oh.
Well, that's what I'm saying. It's our model. We don't know that it's real. We know that we can predict the probability of where an electron is, and then when we use our instrumentation, we find it. We know that we can take an electron scanning microscope and see that dot, but is that because we programmed it to see the dot, or is the dot really there? I don't know. It's as you elevate, is the black box telling you what's there, or are you telling the black box what's there? It's hard to tell. That's part of the black body problem, is what's actually going on in the little black box. And mathematically, we describe all that. We know mathematics works when we build the bridge, right? Because if we don't build it right, the bridge collapses with people on it and a whole bunch of people die. If we build it right, beyond what it's supposed to, the capacity based on mathematics, it works. When we look at the periodic table and we create new elements, which they do at Berkeley, real or not real, they have evidence of them, and they're where they're supposed to be predicted, and they have the physical properties of what's predicted. So we say that's real. It fits into our body of knowledge that we hold as universal, a universal truth based on the 5% of the universe that we know. Does that mean that it's real? No, but it's our best model. But if this is our best model and you don't believe it, then how can you believe anything based on the models that come from this model, right? It's just a method of describing the world that we've used to give ourselves cell phones, a better way of, well, allegedly a better way of life than hunting and gathering. It's a great question. I mean, that's what you do when you're a doctorate. You just walk around thinking about things like that. Is it real? Hopefully somebody will pay you. Otherwise, it's just the discussion you have at a bar with your friends on a napkin, and you don't get any funding. And if you piss off de Broglie or Heisenberg or Seagram, piss him off. Any of the Edward Teller, if you piss any of those guys off, you don't get any money. If you go to a new naval station and you're supposed to build explosives and you piss off the manager, you don't work again, right? Because they control the funding. You have to watch your mouth in every job, right? There's always that one person that you really want to tell them what you think of them, but if you do, there it goes. But there's also a lot of people that'll let you off the record, call you out on who you are, right? And they don't care. But you got to be able to navigate that situation. So, anything else about that? No. Yeah. So it's squared. This is squared. But this is not squared, right? This is this second derivative. I know, right? Looks like squared, but it's a second derivative. Okay. So now let's talk about what those quantum numbers are that describe that association. So every quantum number is defined, right? There are three spaces. You have the principal quantum number. That's the n on your chart, right? So as you go down, each row has an n value, the principal quantum number. So n equals 1, we know it's anything in the first row. N equals 2, anything in the second row. N equals 3, anything in the third row. But anything in the third row also has all the electrons from the second row and the first row. When you get to the fourth row, it has all the electrons from the third row, the second row, and the first row. When you get to the fifth row, you have fourth, third, second, and first. So we're just adding one electron at a time as defined by these three numbers. However, there's a fourth number too. We'll get to that. So n, principal quantum number, n equals 1. Then you have the angular momentum quantum number, which is L. And there are rules associated with that. And then we have the magnetic quantum number, m sub L. So those are the three pieces that define where that electron is in space and what its position around the nucleus is. N, L, and M. And there are rules. So this whole class is a bunch of rules. It's like a board game on steroids, right? Because from generation to generation, we played this game with the universe, where we try to manipulate the known resources of the universe to improve the condition of life for mankind. But it's not just a video game. There are real consequences. And every time we do it, right now we're doing that game with lithium to make batteries. It's going to make a small group of people have a very, 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 very good life. But what will it do to the rest of us? The rest of us don't have a spokesperson. Although we just have Twitter. Twitter's back. Musk got Twitter, so people can say whatever they want again until he increases the value of it and sells it to somebody else.
You mean he's gonna let Trump have his Twitter back?
Who knows?
Who knows?
Can't
I mean, allegedly.
It's gonna be hilarious.
I don't know. I mean, he's going to let a lot. I mean, if it's real, if what he's saying is real, then he's probably going to use it to pump up Tesla stock and Bitcoin. I mean, that's my thought is if I invest billions in Bitcoin and it's not really changing value, then I buy the world's biggest platform and I say Bitcoin is the next hot thing, and then, all right, so, but he really could be about free speech. So when we picture these things, right, we have a probability. And this is what I'm talking about probability. This is the sphere we're looking at, right? So this would be the S shape, the lowest first orbital. So in column 1, column 2, this is the shape of where the electrons are around the nucleus. And it's a sphere. But we don't need to worry about that for us. We don't have to worry about the distribution, except to say that the farther it is away from the nucleus, the less likely it is to be found, right? Because it's going to leave. So if you're skip that part. Let's just talk about n. The principal quantum number n equals 1, 2, 3, 4, 5, all the positive integers all the way down the table. N determines the energy of the electron. So the bigger the n number, the more energy in the electron. It determines how far from the nucleus the electron is, the size of the orbital. So 1s is this big, 2s is this big, 3s is 3 of them, 4s is 4 of them, etc. Right. So the bigger the orbital, the farther away it gets from the nucleus and the higher the energy. All electrons from the same N are said to be in the same principal shell. So if you're in shell 1, you're in energy level 1. Shell 2, 2. As you get to energy level 5, all electrons in the 5N orbital are in that one group and called the principal. And the ones in the 4 aren't in that principal. They're only the ones with the 5N. So L is the shape. So we have M, L, and M sub L. N, L, and M sub L. L is the shape of the quantum number. Allowed values of L are 0, 1, 2, 3, all the way to N minus 1. So for an example, if we're in the 4th N level, right? So the 4th row, what are the possible shapes that we can look at to see where the orbitals are? So L could be 3, 2, 1, or 0. Those would be the allowed states. Minus 1 is not an allowed state. Now, yes?
Are we learning about, we're doing the, like the S1D?
Yeah, we're going to be doing the electron filling, yes, based on these orbital values. So the L describes the shape of the orbital. We call 0 the S orbital. So at 4, 0, we're talking about the 4s orbital. At 4, 1, we're talking about the p orbital. At 4, 2, we're talking about the d orbital. And at 4, 3, we're talking about the f orbital. So those are the shapes, S, D, S, P, D, F. All electrons with the same L are said to be in the same subshell, which means they have the same energy. And it will keep moving. So this is the shape of L equals 0, an S orbital. So the probability of finding S electrons are in this sphere. Right? If we look at the L equals 1, that forms what we call a p orbital, and they're a half sphere with a plane of symmetry through the middle, and which means we can find it most of the time within this framework for this particular orbital. Then we have a quarter sphere, which is the d orbital, with a plane of symmetry again through the axes, and you can find your electrons in there. Now, M sub L, so now we've defined the quantum number, the shapes, and we're going to look at the orientation, like px, py, pz. So how many ways can a sphere orient in space? A dumbbell, a cloverleaf being the D. So L equals 0, the S sphere. M sub L equals 0. There's only one orientation. Why? Because the values of M sub L are 0, plus or minus 1, plus or minus 2, plus or minus 3, all the way up to the value of L. So if L is 0, the value of plus or minus L is 0, so there's only one orientation for the sphere. If we go to L equals 1, right, now we have minus 1, 0, and 1. There are 3 possible orientations to find these electrons. And guess what? There are 3 orbitals, or subshell. There's 3 subshells in the p orbital. And what does that mean? That means one's going to be oriented at the minus 1 direction, one's going to be oriented at the 0 direction, one's going to be at the plus 1 orientation.
Would 2E be 5 orientations?
Yes. Out of the way. I got a plant in the audience. So for D, which is the value of 2, there's minus 2, minus 1, 0, plus 1, plus 2. And there are 5 orientations of this half sphere, or quartered sphere. And then this is the strange one. This is one of the strange ones, the DC squared. But this is where you can find those orbitals, and if you put them all together, they look like a big sphere, don't they? So 5 orientations. So we can either have S, P, D, or F. So how do orbitals change within? Two ways. You got the orbital size and the number of radial nodes. We don't need to worry about that right now, so let's skip that. Here's what we need to look at. What does this mean when we have an s orbital? So we have n, 0, 0, 1 shell. If we have n equals 2, we have L equals 0 or 1, so we have the s orbital and 3 p's, px, py, pz, is for a total of 4. And then, what do we have here? 3, we have 0, 1, and 2, and now we have the s, the px, py, pz, and then the 5d iterations, for a total of 9. But we're still not quite there. For an electron in a specific orbital with quantum numbers n, l, and m, the designation is NL, m sub L, where L is the letter designation, ML is the axis label. So the examples of that are 3s, 4pz, 3dxy, 2dxz. So example, what orbital type has n equals 5, L equals 2, m sub L equals minus 2? 5D, and m sub L doesn't directly relate to x, y, z direction. So what does that mean? It means that it's one of the 5D orbitals. And we're just saying it's the minus 2, which doesn't necessarily make it one of the orientations we looked at before. Not great, not my best work there. Draw an electron orbital with n equals 4, L equals 1, and an xy nodal plane. So we're not going to do that either. But we are going to do this. Which of the following sets of electron quantum numbers are not allowed? All right, so here we have n equals 4, L equals 2, and I've already got it there, so m equals 0. Well, that makes sense, right? Because L is less than 4, which is reasonable. It's a positive number, so that's reasonable. M sub L is 0, which is one of the allowed states. What are the allowed states? 2, minus 1, 0, 1, and 2. So this is an allowed state, right? We can find an electron in that bunch. How about this one? N equals 3, L equals 0. So far, so good. That's L equals 0 is the s orbital. But then we say m sub L is minus 1. Well, you can't do that because
It can only be 0.
it can only be 0. Okay? You with me? Everyone see that?
Yeah.
Okay. We'll go to the next one. N equals 2, L equals 3. No, because L has to be 2 or less. So not allowed. And we can forget about that. N equals 5. L equals 2. Okay, so far so good. M sub L equals minus 3. No, because M sub L has to be minus 2, minus 1, 0, 1, or 2. So M sub L has to be in that range, and it's not. Then N equals 3, L equals 3.
Mm-hmm. No, doesn't work. Has to be less than
N minus 1, right?
Okay.
L must be less than N. Okay. So that's defining where the electron is in relationship to the nucleus. N, L, and M sub L all describe the spatial properties of electron orbitals. But there's one additional property that requires a new quantum number. Z. Odd atoms have a curious magnetic behavior like silver. And what is this up and down property of electrons? Well, we're going to call it a spin orientation. So it either spins one way or the other, and one more thing, and then we're done. Forget it.
Can you go back to that slide so I can fill out the not allowed and allowed when once you're done?
Okay. All right. We'll talk about the last spin number next time.
No, I just have one more to do.
So we'll stop right there. Then we have a lot more fun to do. You guys get to listen to me for another hour or so. I know it's what you wanted to do.